Good morning, students. This particular part of the course is Cauchy-Riemann equations. Like, how do we know that an equation is Cauchy-Riemann? So we're going to solve a couple of questions after getting to know how an equation can be Cauchy-Riemann. So looking at this now, you see that Cauchy-Riemann actually have to like it applies when it comes to complex numbers. The function f is a function of a complex number z composed of a real part u of s comma y. This is a real function actually, a function having s and y plus I v of s comma y. So this I now is imaginary part. So v of s comma y is the imaginary part of the function. So normally we know that our z is equals to s plus iy. Whenever you see CR means Cauchy-Riemann. So in exam you may not be told, but CR whenever you see it means Cauchy-Riemann equations. And you see we have our ux equals to uy. These are the conditions now for an equation to be Cauchy-Riemann. So when you differentiate u with respect to s once, you have ux. Differentiating v with respect to y once, you have vy. So they have to be equal. That's the first condition. Second condition is that when you differentiate u with respect to y once and differentiate v with respect to s once, this thing should hold. Yeah, remember there's a negative sign here. It should hold. So that's part of these two things now are the conditions that make an equation to be Cauchy-Riemann in nature. And it says, and if u of s, uy, vs, vy are continuous and c are the whole at the point, then f is complex differentiable, analytic. Yeah, almost all equations that follow Cauchy-Riemann are analytic in nature. So sometimes they may not even ask you whether it is Cauchy-Riemann. They may just want to a kind of just ask you which of the following equation is analytic. Just perform the same Cauchy-Riemann process, you still get your answer. So they're asking the same thing. So either case, whether they ask you whether the equation obeys Cauchy-Riemann or whether they ask you whether it is analytic, they are both the same thing. So it now says something. So when analytic, f prime of z gives you u sub x plus I v sub x. Yeah, whenever it's analytic, this thing normally happen. When you differentiate the big function, it will give you this. So that's the thing. But as I said earlier, most of the times they are almost the same thing. There's nothing much to explain. So now we have the first question. F of z equals to z squared. We want to find out whether it is Cauchy-Riemann. Now we cannot find out without knowing what z is, because normally the function has to be composed of real parts and then imaginary parts, and they gave us f of z instead of what f of s comma y as we saw here. Okay, this is actually f of z here, but we're going to replace this z now by what it is, s plus iy. When you do that, you see that the z square now we want to replace it, we have s plus iy raised to the power 2. So when you open these brackets, if you don't understand, you can ask me a question. I will show you how I did it later. When you open these brackets using maybe Pascal triangle or normal expansion, you have x squared minus y squared plus I open bracket 2sy. Yeah, that's what this thing will give you. When you expand it by normal expansion, it will give you this. So looking at this now, you see that we now have both real parts and imaginary parts. And I told you earlier that the real part is, the real part is u of s comma y. So this is the real part. So you see that we now name it u of s comma y. Then the imaginary part is 2sy. So you see that we are naming it v of s comma y. Now, having gotten these two values now, we need to find out what our us vy is, and then as well as find out what our uy and vs is. So look at this now. To find out our ux, we need to differentiate this with respect to x, keeping y constant. Keeping y constant. Y is just like a number. So we're not looking at y, we're just looking at x alone. So when I differentiate x squared, I should be able to get 2x, right? So x squared should give me 2x. Because of 2 is here now, it will go to the front and then you remove 1. You have 2x. y is just a constant, it will become 0. So if I want to get my uy from the same equation, I will now keep x constant and work with what? Y. When I differentiate my y, I will have 2y. But remember, there's a minus sign there. This minus sign making it minus 2y. The same thing we apply it to v. V sub x, that's differentiating v with respect to x, we have that this is 2sy, right? When you differentiate with respect to s, the s power is 1. The 1 will go to the front. 1 times 2 is 2. You remove 1 from x, from that power on that x, which is 1. You have s to the power 0, which is automatically 1. So anything to the power 0 is 1. That's why you see that in this thing now, there's no s there again. There's no s again in that place because the s has gone. So you repeat the same thing for this one with respect to y. You will get 2x. Okay. Moving forward to compare these two. Comparing this as we were given, the condition was that u of s have to be equals to vy. You see that they're equal. 2s is equals to 2x. You see that? Then the other condition is that uy have to be equals to negative vx. So minus 2y equals to negative vs, which is what? Minus 2y as well. So if you put minus here, these two will be the same thing. That's the condition. So you see that automatically this thing solves what we wanted. And as I said here, it's analytic. Yeah, it's actually analytic. So it holds everywhere. And partials, say it holds everywhere. And partials are polynomial. This is big grammar. Just know that as far as this thing is it obeys Cauchy Riemann, it would always be analytic. It would always be analytic. So don't forget what I said. If you ask in exam about analytic and they didn't mention Cauchy Riemann, they're saying the same thing. So that's it. So if you need to get f prime of z, what you just do is this. That equation that I gave earlier. Put your ux and vs into this place now. You will get your f prime of s as this. You get. So you may now work for that, factor out, and then get in terms of z. So that's just it. There's nothing there.